Hello, my name is Jun Gun Kim, and I am from Postec, South Korea. I will present our paper titled, Deep Cost Ray Fusion for Sparse Depth Video Completion. Various depth sensors are widely used in several applications, such as augmented reality and autonomous driving. However, these sensors often face the challenge of missing measurements in depth images. Depth completion aims to estimate these missing depths by using both an RGB image and the available depth data. When sparse depth samples are used as input for depth completion, we refer to this task as sparse depth completion. Numerous deep learning-based methods have been developed for this purpose. However, most existing approaches primarily rely on a single view or GBD image as input, rather than leveraging video information. A few studies have attempted to use video information for depth completion. Podol et al. applied convolution for image feature fusion through image warping, while Wang et al. employed spatiotemporal convolutions to capture temporal information, without relying on explicit warping operations. Although these depth video completion approaches produce temporally smooth depth outputs, they have shown lower accuracy compared to state-of-the-art single-view methods. Our goal is to design a learning-based framework that effectively leverages temporal information for depth completion. We assume that the input RGB and depth video pair is captured by calibrated cameras. The output of our framework is a completed depth video. To enhance depth completion using temporal fusion, we perform volumetric fusion in the form of a cost volume, which contains probability distributions used to determine the final depths. Unlike previous image feature fusion methods, our volumetric fusion does not rely on predicted depths and is seamlessly performed by resampling in 3D space. This avoids the warping errors commonly caused by incorrect depth predictions. Next, I will explain how we fuse to temporally adjacent cost volumes. Essentially, we employ transformer-based attention, which has been successfully applied in various fields. A straightforward approach might be to linearize all voxels in the cost volumes to create feature sequences and apply attention. However, such a global fusion is impractical due to the significant memory and computation required. Instead, we propose a ray-based attention mechanism, where we treat ray features as the minimal unit for attention. Ray features refer to the voxel features that a ray intersects within a cost volume. Why did we choose ray features? Ray features contain a probability distribution that is subsequently used to determine the depth of a pixel. By using ray features, we ensure that the entire distribution is considered during the fusion process. Now that I've explained our key idea for fusing cost volumes, I will briefly walk you through the overall pipeline of our framework. For more details, please refer to our paper. Given an input or GBD image at time t, we first estimate a cost volume at time t using a modified version of cost DCNet. We then fuse the current cost volume with the previous cost volume. For the overlapping regions of the two cost volumes, we apply our ray-based fusion method to obtain a fused cost volume. Once we have the fused cost volume, we convert it into a probability volume, which is used to regress the completed depth. Finally, we refine the regressed depth using NLSPN with some minor modifications. Our training process involves two phases. In the first phase, we train all components except for our ray-based fusion module. In the second phase, we train all parts of the framework in an end-to-end manner. Our training objective consists of two loss terms, depth loss and cross-entropy loss for probability volume supervision. This table presents the results of our ablation study on various components. As highlighted in the red boxes, our fusion module significantly improves performance with only an additional 0.08 million parameters. Here, we show the completed depth maps and their corresponding error maps. As you can see, our framework produces more accurate depth maps compared to other state-of-the-art methods. This is a quantitative comparison on the void dataset, where we achieve SOTA performance across all metrics. Even in a single-view setting, our method outperforms the current SOTA approaches. Here, we display the depth video completion results from our framework alongside those of other SOTA methods. As you can observe, our results are both more temporally smooth and accurate than the others. In conclusion, we have proposed a learning-based framework for sparse depth video completion. We introduced array-based fusion scheme to effectively utilize temporal information, resulting in improved depth completion performance. While our framework demonstrates strong completion accuracy, it does have some limitations. The framework requires a high memory footprint due to the 3D convolutions and attention map computations. Additionally, our fusion scheme is not helpful when persistent depth prediction errors occur over time. Thank you for listening.